In this video, we're going to be talking about rotational dynamics. So rotational dynamics is basically where you start explaining what causes rotation. So when we got to dynamics, we explained how forces cause rotations, and now we're going to learn how torques, or what's sometimes called moments, cause rotational motion. So the torque or moment of a force is a measure of the tendency of that force to cause rotation or to rotate about some axis. Okay, so for example, we're going to consider a rod. So now we're still talking about rigid bodies. So if we want this rod to rotate about some pivot point at this pin, then we need to apply a force. Okay, so we need to apply a force that's kind of perpendicular in a way, but this rod is going to rotate, and when it rotates, it's going to form it's going to go through a circular motion. And so the force that we need to apply is tangent to this rod. Okay, so we can turn this into a formula. Our torque is going to be represented with the letter tau. Okay, so this is a Greek lowercase tau. And the torque is equal to this distance r, which is the distance between the axis of rotation, or this pivot point. Okay, so this is our pivot point here. So pivot or axis of rotation. It's the distance between the axis of rotation and the force. Okay, but not all forces will cause rotations. Okay, so specifically the force that is tangent to this circular path that this rod wants to take, that's the component of the force that's going to cause rotations. So for example, if you had a radial force, so you pushed on this rod to the left, or maybe you pushed on it to the right, this radial force would not cause rotation. So if this was, say, F radial, or along the radius of this circle, radial forces do not cause rotations. Okay, so only the perpendicular component to R, or in other words, the tangent component of the force to this circular motion, will cause a rotation. Okay, so really quickly, our units of torque will be the units of force times distance, or Newton meters. And you've seen this unit before when we talked about energy, and we called this a joule. But when we're talking about torques or moments, we don't call this a joule, we just leave it as the units of a force times a distance, or a Newton meter. So say we have a rod, copy this so they're the same, and there's a force being applied at the end of these rods. So it is a force being applied at some angle. Okay, and this is going to rotate about some pivot, so some point on the left. And if we want to find the torque of this force, or the moment of this force, then we need to do one of two things. So there are two ways to do this. So the first is we can use this formula that we found before. We can use tau equals r times the tangent component F, or we can use another formula, tau equals r times F times sine of phi, where phi, it's another Greek letter, is the angle between r and F. So you can treat r and F. F is obviously a vector, but r is also a vector, and it points from the axis of rotation to wherever you're applying the force. Okay, so let's go through this. The first way, say we're given this angle theta. Okay, then we need to find the tangent component of the force. Well, this rod is obviously going to rotate in a circle like this, so the tangent component is going to be right here. Okay, so that is the adjacent side of this right triangle. So if we wanted to find F tangent, the tangent component, we could do F times cosine of theta. Okay, then we would just do tau times R, or equals F tangent. So tau equals R times F tangent, where F tangent is F cosine theta. Okay, so you could find your F tangent and then plug into this formula. Okay, or we can use this second one, but we have to be careful about this angle. This angle theta is not the angle between R and F. Okay, so this is not phi. This is the angle between F and some vertical line. If you want to find phi, then you start by drawing your vector r. So r points from some axis of rotation, and it's pointing to the right. And then you go back to that point where you started drawing r, and you draw your force vector. Okay, now this angle between r and f, this is your angle phi. So if you can find this angle, then you can just plug into tau equals RF sine phi. Okay, so in this case, you know this angle is theta. Okay, so if you were given theta, then phi would equal 90 minus theta. Okay, and so this is also the same thing. So F sine phi, this is just another way of getting the tangent component of F. Okay, but if you want to use this formula, tau equals R sine phi, you have to make sure that you're using the correct angle. So sometimes you will be given the angle between the vectors R and F, and you can just plug into this formula right away. However, if you're given another angle, you either need to use that angle to find F tangent and then plug into this formula, or you need to use that angle to find the angle phi and then plug into the second formula. But both of these are ways to find your torque. Okay, so let's just sum that up really quick. So if we wanted to, the first option would be to find F tangent with our angle that's given. Okay, and then we use tau equals R times F tangent. Or we could use what's given to find the angle phi, which is the angle between R and F. So between the vectors R and F. And then we could plug into tau equals RF sine phi. And in my opinion, this is always the easier one to do because it usually just involves some basic geometry. Okay. Now R, just for some language, this is sometimes called the moment arm or the lever arm. Okay. And now some notes, things you want to keep in mind. The angle, so we've already mentioned this, but the angle given in many problems may not be phi. So if you want to use phi, you need to go find it if it's not given. The vector r points from the axis of rotation, okay, you can't emphasize this enough, to where the force is applied. Okay, and then only forces, so I'm going to write this, I'm going to say this two different ways, only forces or force components tangent to the circular motion, so circular path, which is the same thing as the components that are perpendicular to R, so you can say it either way, cause rotation. Okay, I prefer to think of forces perpendicular to R. Okay, and the easiest way to remember this or to see it is to visualize a door. So if you have a door with some hinges on the left, if you were to push along the door, so along the narrow end, that's not going to cause it to swing open or close, so you're not going to rotate it either way. Okay, but if you pushed kind of perpendicular to the door, that's going to cause it to rotate around this hinge. Okay, not only that, but if we write down our formula, so F tan or R F sine phi, okay, if you were to push at the hinge, that corresponds to R equals 0. So there's no torque, and that's why if you push on the hinge of a door, it doesn't open. If you get further away, so you increase R, you will also increase your torque. So the further away you get from the hinge, the more torque you're applying, the easier it is to rotate the door. So this is why the handle of the door will always be on the opposite side of the hinges. Okay, it's the furthest away, so it's easiest to push. Okay, so your torque gets stronger, or it's easier to rotate the further away you are. If you push at the hinge, there is no torque. And then if you push along the door radially, it doesn't cause any rotation, so only forces that are perpendicular are going to cause rotations. Okay, and so the last thing you need to remember is the directions. So just like anything in rotational motion, positive corresponds to counterclockwise. So positive torques will cause counterclockwise rotations. Negative torques will cause clockwise rotations. Now let's talk about Newton's second law, but the angular version, so the Newton's second law for rotational motion. Okay, so for rotation. So before we had the sum of the forces is equal to the mass times acceleration. Well, now, rather than going through a derivation, we can just replace all of our linear variables with angular variables. So we'll get the sum of the torques instead of forces is equal to, instead of mass, we had moment of inertia. So mass gives objects inertia, which is resistance to linear motion. The moment of inertia is resistance to change in angular motion or rotational motion. And then instead of linear acceleration, we have angular acceleration. Okay, so mass, or what gives objects inertia, goes to moment of inertia. Acceleration goes to angular acceleration. And then forces become torques, or torques of forces. So we say the torque of a force. Okay, so now let's talk about work and power. So our formula for work, for linear motion, we had the work was equal to the force times the displacement. And in rotations, if you're going through some arc length, some delta S, that corresponds to R times delta theta, assuming that R is constant. And so if you plug this in, you get the work is equal to F times R delta theta. Well, we know FR, this is just our torque. So we end up getting the work is equal to tau times delta theta. So these two look very similar. Instead of forces, you have torques instead of a linear displacement. So delta S is a linear displacement. Now you have delta theta, which is angular displacement. Okay, so this is our formula for work done by a torque. And then we can easily get our expression for power. So average power is just the work done in some interval of time. If we plug in this formula that we just got for the work, then we get tau times delta theta over delta t. But delta theta over delta t, that's just equal to omega, okay, or angular velocity. So our formula for power becomes the power, or average power, is tau times omega. And this is similar to our expression from linear motion. The power is equal to the force times velocity. In angular motion, instead of forces, you have torques, and instead of velocity, you have angular velocity. So let's continue on with our angular quantities. Okay, we're pretty much going through all of the quantities that we had for linear motion and getting angular analogs. So for angular momentum, let's go back to how we introduced momentum. First of all, we said that Newton's second law, F equals ma, wasn't how he actually wrote it. He actually wrote that the sum of the forces was equal to the change in momentum over the change in time. Now we have the sum of the forces, or the sum of the torques, is equal to I alpha, so moment of inertia times angular acceleration. And if we take our Newton's second law in terms of momentum, and we just multiply by r on both sides, well, that gives us torque. F times r would give us torque on the left-hand side. And we're going to call that quantity P times r our angular momentum, and it's going to be given the letter L, the variable L. So this is the change in angular momentum over time. So this means that L is equal to r times P, and we're going to call this angular momentum. Okay, or sometimes this may be written as L equals mv, so that's just our definition of momentum, mass times velocity, times L. Okay, so little l instead of r, but it's just a distance. Okay, in the same way that you have r, some distance from axis of rotation for all your other rotational quantities. So our units of angular momentum are kilograms times meters squared per second. And this definition of angular momentum is typically used for a particle. Okay, so I'll make a note of that. The angular momentum of a particle is typically given using this formula, L equals mvl, or r times p, however you want to write it. But for a rigid body, we typically use a different formula. Okay, so if you look at our linear momentum, so P equals mv, if you replace all of these with just their angular counterparts, we get L instead of linear momentum, we get angular momentum. Instead of mass, we get moment of inertia. And instead of velocity, we get angular velocity. Okay, and so this is the formula we use for angular momentum of a rigid body. Since particles don't have moments of inertia, we use this formula. Okay, and then if you did this for every particle, you could show that that's equal to L equals I omega for a rigid body. So just like with linear momentum, we got a conservation law. We also get conservation of angular momentum. Okay, and so I want to talk about what types of problems you might use conservation of angular momentum to solve. So The statement of conservation of angular momentum says that your final total angular momentum is equal to your initial total angular momentum. So typically this looks like your initial moment of inertia, or final moment of inertia, times your final angular velocity is equal to your initial moment of inertia times your initial angular velocity. Okay, and so unlike in regular momentum problems, where your mass doesn't change, it's typically your velocity, now both your moment of inertia and your angular velocity can change pretty easily. And so some examples of where you might use conservation of angular momentum. So we always tend to use conservation of momentum when we have things like collisions and problems like that. We want to use conservation of angular momentum if we have a problem where mass gets redistributed. So this would change your moment of inertia, so it changes how your mass is distributed. So an example of this is you have an ice skater that is spinning, and then they kind of bring their arms together, and they take their arms from being way far apart and away from their body, and they bring them up where they're much closer. And so they effectively change their moment of inertia. And so that's why they start to spin faster. And so both their moment of inertia and their angular velocity change. Okay, you can also have an analog to collisions. So you can have collisions between objects that are rotating, or that rotate after a collision. So maybe they weren't before, but they rotate after the collision. Make that an A. Okay. So an example would be if maybe you dropped so maybe you have a spinning wheel like a potter's wheel, and you were to drop a big ball of clay near the edge. Okay, so now you just kind of added mass to the outside, so it effectively changed the moment of inertia. Okay, so that's a classic problem. And you may also have something where, say you shoot a bullet into a hinged plank. So these seem like very specific examples. So say you have a bullet and you're shooting it into a hinge, a plank that's hinged, and then it starts to rotate. So the bullet kind of gets embedded into the plank, and then it kind of is rotating this way. Okay, so before they weren't rotating, but now they are, and so these objects have angular momentum, and this was a collision much like the collisions when we used conservation of linear momentum. So we'll do some problems like this in a future video where you can see exactly how we use conservation of angular momentum to solve some problems. So now I want to talk about static equilibrium. So we mentioned equilibrium when we were talking about forces, but then we only considered particles, and particles couldn't rotate. Okay, they have to have another dimension to rotate into, and particles are just one-dimensional. Okay, so when we had just particle equilibrium, all we needed was the sum of our forces in all directions, so in x and y, to equal 0. And this corresponded to no translational acceleration. So if the sum of the forces are 0, you're not going to accelerate to the left or right, up and down, anything like that. But now that we're considering rigid bodies that can rotate, we also need the sum of the torques to equal 0 for a body to be in equilibrium. And so this corresponds to no rotational acceleration. Okay, so for a body to be in equilibrium, static equilibrium, it must not have any type of acceleration. Okay, so this implies that AX equals 0 and AY equals 0. And then the sum of the torques equaling 0 implies that our rotational acceleration, alpha, is 0. And it's important to note the sum of the torques about any axis. So you could pick any axis, it doesn't matter. And if you sum up the torques about that point, they should equal 0. So for example, if a door is in equilibrium and it's not rotating, it doesn't matter which point on the door you pick, none of them are rotating, and so they must all be in static equilibrium. And so a lot of times it's convenient to pick a point or an axis that makes your math much easier. Now I want to talk about torques from gravity. Okay, so all objects that have mass feel the gravitational force of the Earth, namely their weight. And so we need to know how to treat the force of gravity in terms of torques. And the way we want to treat it is as though the weight is acting as a single force. So even though the weight of every single particle, there's a force from the Earth pulling on every single particle in a rigid body, we want to replace all of those with a single force, the total weight, acting at the center of mass of that object or that rigid body. And when you do this, this is often called the center of gravity. And so the torque from gravity is equal to the total mass times the gravitational acceleration times the distance to the center of mass from the axis of rotation. So this is the distance from, again, the axis of rotation. It's good to repeat this over and over so you don't forget, to the center of mass or center of gravity. Okay, so you can kind of use those interchangeably, but I do want to make a note, and you could review our center of mass video. Center of mass and center of gravity are technically different, and you can find the center of mass, so you can calculate or define the center of mass even in the absence of gravity. Okay, so they correspond to the same point or the same location on an object, but they aren't technically the same thing, so just be careful with that. So now I want to talk about the direction of all of these angular quantities. Okay, so we've been kind of treating all of these angular quantities like omega and alpha, angular momentum, torque. We've been kind of treating them like they are scalars, and I haven't really been putting vector hats on them, but in reality, these are all vector quantities. Okay, so these are vectors. And vectors have not only a magnitude, but a direction. So how do we get the direction? Well, in order for these things to rotate, they have to rotate about some axis, so they need some third dimension. And so we get the direction from something called a right-hand rule. So we always use right-handed coordinate systems. So this is sometimes abbreviated RHR. So the right-hand rule says to curl your fingers in the direction of rotation. Okay, so if the torque, it's what direction would the torque cause rotation, and so on. And then your thumb points in the direction of that angular variable. So points in direction of the angular variable or the angular vector. So if you take your right hand and draw a thumb, then you've got some fingers. So say they're curled in like this. So they're curled in like this, then your thumb points in the direction of the vector. So maybe a better illustration would be to draw a disc, and if this disc is rotating clockwise or counterclockwise, so it's rotating like this about the center, then if you were to stick your fingers and curl them in the direction of rotation, your thumb would point straight up. And so this would be the direction of, say, your angular velocity. We define it to be normal to this plane, or using a right-hand rule. Okay, the last thing I want to talk about is something for students taking physics with calculus. So if you're taking general physics without calculus, this doesn't apply, and you can move on to the next video. But for people in physics with calculus, all of these, not all of these, but some of these angular variables can be defined in terms of cross products or a vector product. Okay, and so our angular momentum, instead of just r times p, it's actually defined as r cross p. And the torque is defined as r cross f. Okay, and so this gives us another way to find these angular quantities. And typically, when we use the cross product, we need our vectors, so our vectors r, p, f, to be in Cartesian form. Okay, so Cartesian form just means we need them to be written in the form. So for example, a force vector would need to be in the form of the x component times the unit vector I hat plus fy times j hat plus fz times k hat. Okay, and so for example, our tau, or torque, would be rx I hat plus ry j hat plus rz k hat crossed with fx I hat plus fy j hat plus fz k hat. Okay, and then we could evaluate this cross product to find our torque. And so the easiest way to do this is to distribute. So the first term, for example, we would get rx times fx, and then our I hat would be crossed with our I hat plus rx times fy. So these are just scalars, so they can't be crossed. But I hat, j hat, k hat, these are vectors, namely unit vectors, so they can be crossed. So this is I cross j hat, and so on. And all you have to remember is that I hat, j hat, and k hat are cyclical. So as long as you cross them in order, you get I hat cross j hat equals k hat, j hat cross k hat equals I hat, and k hat cross I hat equals j hat. And you also get, since I and I are parallel, then if you cross any unit vector with itself, you just get 0. Okay, so this is one way, and often the easiest way, to evaluate a cross product and find these angular variables. But you can also use the determinant of a 3x3 matrix. Okay, and so you can do this by putting your unit vector in the top row, and then put the x, y, z components of your vectors in order. So r in the second row, and then your force in the last row. And you can do the same thing for angular momentum. So again, your unit vectors in the top row, and then r in the second row, and p in the last row. So x, y, z components of momentum. And you can evaluate this 3x3 determinant to determine, so this is the determinant, 3x3 determinant, to determine these angular quantities or evaluate your cross product. So I have a video completely on the cross product and how it's defined and how to evaluate not only this 3x3 determinant, but also if you wanted to do it by distributing. I have a video on that going through it, as well as some example problems. So if you're not familiar with cross products, you may want to start there first, but know that these angular quantities are actually defined in terms of a cross product, and you will probably see this in class if you take physics with calculus. So I hope this video helped you understand some of rotational dynamics and how things are defined, how we go from linear variables into angular variables. And in the next video, I'll have a bunch of example problems where we actually go through and find all of these quantities. And so I'll see you in the next video.